Okay, let me just review really quick here. And do you remember what this angle was called right here? We had a special name for that angle. What was it? The angle, the actual angle. What was it? Somebody, I heard it. Central angle. The central. Okay, why is it the central angle? Because where's the vertex of that angle? It's at the what? The center of the circle. Okay, that's pretty easy, isn't it? Okay, it's the center of the circle. It's the central angle. What do we know about the measurement? If this is x degrees right here, then arc is the same thing, right? So arc AB, I'll tell you what, let's not make it x, let's actually make it a real number. Now what does that look like? 60? We'll say 60. So arc AB is equal to 60 degrees as well. Remember, the central arc is equal to the arc, the central angle is equal to the arc that it cuts off. We good with that, right? That was easy. That's one of the first things that we talked about. All right. We're going to talk about another We're going to talk about another angle inside that triangle, or inside that circle, not the triangle. Let's get rid of all this, get rid of all this. Okay, starting from clean slate here. Watch where this angle starts from and goes to. Let's go yellow. That stands out pretty good. Watch this. Look where the vertex of this angle is now. It's not at the center of the circle, is it? It's actually on the circle itself, isn't it? Okay. So this is a point right here, but where's that vertex? It's on the circle. Okay, it's actually on the circle. So the angle comes, or the arc is formed. We'll call it arc AB again. We'll call this angle C. This arc right here is the one that's formed. So let me draw that, because there is definitely significance to this arc. Let me try to trace it around. Oops. Okay, that's not too bad. Rough start, but I got that's pretty good. So let's take a look at this. This angle right here, angle C. Let's just use numbers. I think it's easier to understand if you just use numbers instead of letters and stuff like that. So I don't know, that looks maybe about 40 degrees, maybe not quite that much, or yeah, it's probably a little less. But anyway, we'll say that's 40 degrees right here. Now look at this arc. Now this arc, now I know it's hard for you to kind of visualize like how many degrees an arc is. But if you think about it, if you go halfway, watch, if I started here and just draw an imaginary line to about right there, how many degrees is it from here to here? It's 180, isn't it? Now, again, I don't know if that's exactly 40 or not, so I'm just kind of eyeballing it a little bit. But you do kind of have an idea of how much of an arc is. So how much would half an arc, or half of this half be? It'd be 90, wouldn't it? Half of the half, right? I'm not talking about the 40. I'm just talking about the whole circle, okay? Half of the half of a circle would be 90. Great? All right, so I'm just trying to get you to visualize a little bit the measure of an arc. Now, that definitely doesn't look like 40 degrees around the arc, okay? Because 40 would be less than half of half the circle, okay? Less than a quarter of a circle. And that looks like more than a quarter of a circle. So this is not exactly equal to 40. This is not a central angle. The vertex of this angle is not at the center. It's actually on the circle itself. And I'll give you the word. We call this an inscribed angle. Okay? Call it an inscribed angle. An inscribed angle is when you have an angle where the vertex of that angle lies right on the circle itself. Not inside the circle, not outside the circle. Not even at the center of the circle. Where? The vertex is on the circle. Everybody got that? Put a little dot right there. So it's on the circle. Now, here's the relationship. I'm sure you're dying to find out what this is. This arc right here is actually twice as big. It's exactly twice as big as this angle. That's an easy relationship to remember. So arc AB would be equal to what? Twice that inscribed angle, so 2 times 40, and it would be 80 degrees. So this arc from A to B is 80 degrees. Pretty simple. We're going to use it a lot though. Alright, so make sure that you understand that. It's not hard to do, it's just twice as big. Think about it. If I took this, I wonder if I could do this. Let me see with my little program here. Let's go different color here. I haven't tried this yet. You'll be the first ones I've tried this on. Okay. And what I'm going to do is I'm going to group them together. And let me see, group them, okay. And nah, it didn't exactly do what I wanted it to do. Well, it kind of does. Watch. Watch this angle. That's a pretty wide angle right there, don't you think? Looks obtuse even, doesn't it? See that angle right there? That's what I'm looking at right now. So watch, if I take this, now I can't really take it to this point right here, but that's okay. I can take it to here, watch. Look what's happening to, now if I really extend it, what's happening to that angle? Is it staying the same? It's not. What is it doing? It's getting what? It's getting smaller and smaller and smaller, isn't it? In fact, we just talked about that relationship. So how much smaller is this angle here compared to where it is right here? The angle. This angle right here would be how much smaller? How many times smaller would this angle on the circle be compared to this? What? How much? It'd be, well, it'd be, yeah, I guess I'm kind of saying it wrong. How many times as big? It would be half as big, wouldn't it? That's how I should say it probably. But you're right, it's twice as small, but I don't want to say it like that. That sounds kind of weird. It's half as big. Would you agree? So whatever that angle is right there, I don't know, let's just pretend, okay, it's, well, actually, yeah, it should be 80, shouldn't it? Okay, why should that angle right there? I know it doesn't look 80, because remember, I just kind of eyeballed what this was, and I said it was 40, but let's just pretend these numbers are correct. This angle right here should be 80 degrees. Why is that? Because it cuts off an arc that's 80 degrees. Would you agree? Okay, but watch this though. If I took this and I stretched it to here, now what is that angle? It's 40 degrees now, isn't it? It's half as much as it was. Well, see, I didn't exactly, I mean, this didn't work out exactly the way I thought, but you get the idea. All right, I thought that thing would stay there, but I guess it doesn't. We're okay, but you kind of get the idea. If that was 80 degrees and I take it to here, then that would be 40 degrees. All right, that didn't work out exactly the way I thought, but you kind of got the idea, I believe, of what I just did. What if I did this? Let's keep that same color. What if I started somewhere else on the circle and I drew this to A and I drew this chord to B? Let's say all those numbers are still the same. If that was 40 degrees, then arc AB is 80 degrees. Tell me something about angle D. It's the same thing as this one. Why? Because it cuts off the same arc, right? Cuts off the same exact arc. So if it cuts off an arc that's 80 degrees, we already established that this is 80 degrees. So if this inscribed angle cuts off this arc that's 80 degrees, tell me something about the angle. It's 40, that's right, because it's half of the arc. You see that? So look, if I have, and this is another theorem, this is a second theorem. It says if I have two inscribed angles that cut off the same arc, and they do, don't they? Look at angle D and look at angle C. They both cut off arc AB. See? It goes to A, goes to B. This one goes to A and goes to B. They cut off the same exact arc, so these two angles must be exactly the same. Why? Because you're taking half of the same number, aren't you? They're both inscribed angles of an 80-degree arc. You're taking half of the same angle. Let's just for fun, let's do one more. We'll do this in green. Let's start, I don't know, somewhere way down here, make it real crazy. All right, so watch. If I take this up to A, and then I take this to B, tell me something about this angle right there. That's 40 degrees as well, because again, it cuts off the same exact arc, doesn't it? You with me on that? Okay, so if you have angles, inscribed angles, not just any old angle, if you have inscribed angles that cut off the same exact arc, or equal arcs. I could have two circles here, and I'll do that in a second, okay? I could have two circles that cut off the same arc measurement, then those two angles are going to be the same as well. Because if this cuts off an 80-degree arc, it's 40 degrees. This yellow one right here cuts off an 80-degree arc. It's 40 degrees. This green one cuts off an 80-degree arc, and it's got to be 40 degrees. I could keep going all day, couldn't I? As long as they cut off the same exact arc. We got it? Okay, you're going to be definitely, I mean, you can see what's going to happen, right? They're going to give you the arc and you got to find the angles, or they'll give you the angles, you got to find the arc, and all that kind of stuff. They might give you this. They might say that this angle right here is, I don't know, I'm just making these numbers up. I don't know if they'll come out right or not. But they'll say, okay, this angle right here is 3x plus 2, and this angle down here is 5x minus 7 or something like that. And then solve for x. What would you do if they gave you something like that? You set them equal, right? Because you know those arcs are equal to each other. I'm sorry, the angles are equal to each other. Set them equal, solve for x. Does it make sense? Okay. All right, I think you get an idea there. Let's move on. All right, let's get another circle. And what we're going to do here is this. I'm going to draw a diameter. That's pretty close. There we go. All right, there's a diameter. Now what I'm going to do is we're going to basically do what we did in that last theorem. Okay, I'm going to use any point. It could be anywhere on the circle. I don't care. Let's just use this top half of this semicircle. I don't know. There's no magical place. Let's just start right here. Excuse me. So if I started right here, what I want to do is I want to draw an inscribed angle that cuts off a semicircle. You hear what I just said? I want to draw an inscribed angle that cuts off a semicircle. So what does that mean? That means it's got to go, one of these chords has to go to one end of that semicircle, and then the other chord has to go to the other end of the semicircle. See what I just did? Yeah, very good. You saw it quick. So Nico said this. He said this has got to be 90 degrees then. How'd you get that, Nico? Just because it looks like a 90-degree angle? That's right, you cut off a semicircle. How many degrees is this semicircle? We'll call this A, B, C. Okay, so look at arc ABC. It's half of a circle. How do you know it's half of a circle? Because this is a diameter, right? And a diameter cuts that circle into half. So arc ABC is a semicircle, so this is 180 degrees, this big old arc right here. So what do we know about an inscribed angle? It's half of the arc that it cuts off. If the arc is 180 degrees, this inscribed angle has got to be what? It's got to be half of it, which is 90 degrees. All right, so we made a perfect 90-degree angle just by doing that. I could go somewhere else on here just to show you that that's not a certain magical place. I could, I don't know, start here. Watch. And go to C, and then take this and go to A. Just by doing that, without ever measuring anything, what is my angle up here? This has got to be a 90-degree angle, isn't it? Everybody see that? And of course, these two have to be equal to each other because they cut off the same arc. So that's kind of cool, isn't it? I mean, you can do this all day long and still get a bunch of 90-degree angles. All right, so I don't know, where do you want to go now? Let's go like halfway, see, or it looks like it's halfway. Let's go to here, and then let's go to here. All right, look at that. That's also a 90-degree angle. Isn't that pretty cool? All right, so I could have all these 90-degree angles. It's very easy to make a 90-degree angle. Draw a circle, draw a diameter, draw an inscribed circle that cuts off right at the ends of that diameter, that semicircle. And then you got a 90-degree angle. Perfect 90-degree angle. All right? Okay, let's see what else we got. All right, here's another circle. What I'm going to do here is I'm going to draw a thing called an inscribed quadrilateral. Inscribed. You could do any polygon, but I'm going to specifically do a quadrilateral. Okay, quadrilateral. Kind of small, but you get it. Inscribed. Now, we talked about an inscribed angle. What has to be true about an inscribed angle? The vertex has to be where? On the circle itself. So what do you think about all the vertices on this quadrilateral? Where do you think they have to lie? So watch. Can I do this? Is that an inscribed quadrilateral? It's in the circle, isn't it? Inscribed, isn't that what it means? No. It's got to touch, exactly right. It's got to be on the circle, right. So watch. So that's one chord. See? Every vertex has to be on the circle. Now, I'm not necessarily like trying to draw a rectangle or a square or anything else, am I? I'm just drawing any old arbitrary quadrilateral. It doesn't even have to be a parallelogram or anything like that. All right? It just has to be four sides, and all four vertices, look, 1, 2, 3, 4, all four vertices lie on the circle itself. So that's what I call an inscribed quadrilateral. You say, well, big whoop. Well, it is a big whoop because there's actually, okay, a couple things about this. Look at the opposite angles. Let's do this. A, B, C, D. All right, this is pretty interesting, I think. This is kind of like a parallelogram, even though it's not a parallelogram. Look at angle A and angle C. Are they equal to each other? Nah, look at it. What kind of angle is angle A? It's acute. What kind of angle is angle C? It's obtuse. Is there any way that they're equal to each other? No. But what's a wild guess? No, because they're supplementary. They're supplementary is what they are, okay? So the opposite angles on an inscribed quadrilateral, right, A and C, are supplementary. So if I wanted to write this down, I could say angle A plus angle C is equal to what? 180 degrees. What do you think might be true about B and D? They're also equal to 180. Now, this doesn't mean that these two are equal to each other or anything else, or these two are equal to each other. Doesn't mean anything like that. But watch, these two, that's 3 arcs. Put 4, 1, 2, 3, 4. So angle B and D are supplementary to each other as well. So angle B plus angle D are also equal to 180 degrees. You can definitely see what they're going to ask you on some questions on the homework, don't you? All right, they're going to give you some angles. Now, what do all 4 angles add up to be? 360, okay? No matter if we even knew that these opposite angles were 180, we knew that all 4 add up to 360, okay? All right, let me see. They do give you a couple examples in here. I just didn't hit the examples. Just we're running a little short on time right now. So what I would suggest that you do before you even do the homework is take a look. I went through every theorem that they did in this lesson pretty thoroughly, I think. So it's up to you. Kind of scan through the examples before you actually start on the homework problems. Okay? Let me give you some problems to do. Then you can practice up on these things. Alright, let's see where we are. 10.4, so it's section 10.4. I almost said, well, I'm going to. 10.4, good buddy. That's probably something that most of you have no idea why you even said that or what the significance. If I said 10.4, good buddy, where does that come from? Does anybody know? See, back when I was your age, I mean, everybody was saying that kind of stuff. 10.4, good buddy. It's country. Why is it country? Where's it from, though? From the truckers, right. From what on the truckers?
Something has to do with, like, tracking the people. Like to know where all the truckers are, so you don't rent to each other.
Yeah, but what on the trucks did they use? CB radios, that's right. You ever hear of a CB radio? Okay. Yeah, and it goes over the airwaves and stuff. It's not digital or anything like that. Yeah. So anyway, but back when I was your age, or actually probably a little bit younger, CB radios were crazy. I had a friend. I lived in Newcastle. I lived in Penn Acres, and my friend lived in Swanwick, which is way on the other side of Newcastle. And we would talk, like, this was stupid, but we'd call each other on the phone, and we'd say, all right, at 5 o'clock, we're both going to get on the CB, see if we hear each other. We're going to be on channel whatever. And then, so we make sure we get on the same channel. We talk to each other. Kevin, can you hear me? And I could barely hear him, squeaking in the background a little bit with all this fuzz in it. I'm like, yeah, I'm here. Can you hear me? Yeah, I'm on the radio. Yeah, so am I. It's like, okay, that was it. That was our conversation. It was like stupid, but we were all excited that we could actually talk to each other that far away on the CB radio. So you guys, yeah, it's like a walkie-talkie, but like a real big-time walkie-talkie kind of thing. Anyway, there's my dumb story. I just saw it. When I see 10.4, I always think of that because, they're like, oh yeah, I was going to. Let's do that.